Hello everybody. So we are still looking at inferential statistics, and so we're still somewhat dealing with module 6, and so I put this as module 6b, and what we're going to look at in this module is hypothesis testing. Now if you remember from the last module, we looked at degrees of freedom, standard error of the mean, and then confidence intervals. And so what we were talking about in that is taking our samples and trying to decide how confident we were that the results of our samples could be estimated or inferred to the population. And so we looked at a few statistical procedures to arrive at some data points. We looked at a lot at the normal curve to get this. So in this module, we're going to take it one step further and actually describe how we would state this as a statistician or somebody dealing with statistics in a hypothesis, and then some potential pitfalls with hypothesis testing. And so that's what we're going to look at in this module. So our module goals then are: we want to use the sampling distribution characteristics to test hypotheses about differences between the sample and population means, distinguish between a null hypothesis and the alternate hypothesis, define the significance level alpha of a statistical test, distinguish between one and two-tailed statistical tests and know when each is used, define and contrast type 1 and type 2 statistical errors, and then perform the steps of a z-test of significance at a specified alpha level. So you will find after we finish this module, those things are going to be fairly easy to do. Okay? So moving on. So I like to give you sample some real-life educational scenarios here. So let's say that you are a high school principal, or it could be an elementary principal, and you received the test scores, the most recent test scores, and you had the national mean. You knew what that was, and you were slightly above that mean. And you also knew what your statistics class students did because you're able to disaggregate those data, and they were above the mean. And so you want to ask yourself, are there any differences in these scores? And so that's what we're going to look at and talk about and use as an example here in the first few slides is how would we write this as a hypothesis of what we want to look at, and how would we go about seeing if there's any difference in these scores that are statistically significant. And we're going to talk about what that word means, those words, statistically significant. And you'll find that you have already done in the last module the basic steps to get what we call a z-test of significance done. So we'll look at that as well. So to begin with, let's talk about hypothesis. Okay, and the plural of hypothesis that ends in is is hypotheses, ending in es. Okay, so a hypothesis is simply a conjecture or supposition tentatively accepted to explain a certain phenomenon or a certain phenomena. And so we just state our hypothesis that explains what we're doing or what we think is happening, and then we're going to test it to see if it's true. So in research then, a research hypothesis becomes basically that same definition. A conjectural statement about an unknown phenomena. A statistical hypothesis is we're making a supposition about some population parameter. Okay, and remember, parameters are the descriptive statistics that define a population. And so we're making a supposition about a population with a statistical hypothesis. Okay, we won't refer to that much anymore, but just understand that that's what that means. Really, we're going to concentrate on your research hypothesis. So consider these things. Candidate X would make the best student body president. Venus is inhabited by living organisms. Students who complete a driver's education course subsequently have fewer moving traffic violations than those who do not take the driver's education course. And students in a statistics class at Central High School achieve at a higher level than the average student in the nation. All four of these could be considered research hypotheses. Okay, but if we look at 3 and 4 here a little bit more closely, these are more readily accepted as statistical hypotheses because we are looking at specific things that we are going to measure. And once we measure our samples in these, we're going to make some inference about the population parameters. The last one, sample 4, really is a prime example because it tells us in this one what our population is. So students in the statistics class at Central High School achieve at a higher level than the average student in the nation. So we know what our population is specifically in 4. So that's a prime example of a statistical research hypothesis. So for some further clarifications, as we said, students in the statistics class at Central High School achieve at a higher level than the average student in the nation. We could clarify this by stating, on the average, students enrolled in the statistics class at Central High School will score higher on a standardized achievement test than the national norm. Okay, so we've just rephrased our statement. We got a little bit more clarification in there. We named a standardized achievement test. We're looking at the national norm. So our distinctions here, we clarified the measuring instrument and also the direction for measurement. Okay, so not only did we talk about the instrument, the standardized achievement test, we also talked about a direction of achievement here. And we specifically said these students will score higher. Okay, so those are some important characteristics noted here. And you're probably going to start with that basic first statement that the students in this class achieve higher than the average student. And then we'll work through some clarification. Okay. So in statistics, we actually don't measure our hypothesis. We generate our hypothesis, and then we create what we call our null hypothesis. And that is abbreviated capital H sub 0. Okay, null hypothesis. So our statistical analysis does not actually address the hypothesis. And you will pick up on this in time. Okay, it's kind of a different concept to think about, but you'll pick up on it. So rather what we're actually measuring is the opposite of what we want to measure. So we're measuring a null hypothesis, and the null hypothesis expresses how a phenomenon would occur if only random events were operating. Therefore, it is expressed as a no relationship and no difference. And like I said, this will become a little bit more familiar too as you see some. So an example of this, if you were to flip a coin 100 times, the expectation would be you would get about 50 heads and 50 tails. The null hypothesis would state then there will be no difference between the number of heads and tails. Okay, so our hypothesis is that we will get 50 heads and 50 tails. Our null hypothesis states that there will be no difference between the number of heads and tails. So actually that's what we're measuring, to see if there is a difference or not. And if there's no difference, then we accept our null hypothesis and we're done. Okay, and we're going to get more into this. For our math students at Central High School, we would state there is no difference between the statistics class at Central High School and the national population mean score on the achievement test. Or probably there's no difference between the mean score of students in the statistics class at Central High School and the national population mean on the same test. Okay? Our null hypothesis, we're basically saying mu equals x bar. In other words, our population mean is equal to our sample mean. And that if these two are equal, then there is no difference. So that's what we're really looking to see is, are they equal? And if they're not equal, how much are they off? And that's where we're going to start moving into in a minute, is determining how much they're off is going to determine whether or not we still accept our null hypothesis as being true. So instead of our null hypothesis, what we typically call a hypothesis, we're going to call an alternate hypothesis, which would be abbreviated H sub 1. If we show the null hypothesis is not accurate, we don't prove anything, and we're going to reiterate that later on. In other words, in our heads and tails, statistically that's going to come out as accurate, but let's say we had a sample that was out of the norm and we actually got 70 heads and only 30 tails. Then what we do is we reject the null hypothesis and accept our alternative hypothesis. Maybe we're testing a coin because we think that it's a weighted coin and we want to see if it's a weighted coin, so we're going to do some sample flipping of this coin. Our hypothesis would be something along the lines of there will be more heads flipped out of 100 flips than tails using this coin that's a weighted coin. Our null hypothesis is there will be no difference in the number of heads and tails. So that's actually what we're measuring, is the no difference. And depending on how much difference there is, we will either accept or reject that null and accept our alternative in its place. When it comes to the school students, the alternative hypothesis is what we usually first think of as the actual hypothesis we're trying to show. In our sample of school students, the students in the statistics class at Central High School scored significantly higher than the national mean on the achievement test. This is our alternative hypothesis, and this is how we usually express it. We usually want to show this, but we're going to test the null hypothesis. Okay, so I said that gets a little bit tricky, but the alternative hypothesis, again, is generally what we want to show, but we don't test that. We test our null hypothesis, that there is no difference. So, if we say we test the null hypothesis, how do we actually test it? And then once we test it, how is it rejected? Okay, so that's where we're going to start moving into next. What we're looking for is statistical significance, and this is an important term, and you will hear this term used incorrectly, I believe, many times. The term statistical significance takes on an important meaning in statistics. We are saying under random conditions, the phenomena we are examining would not have occurred. In other words, our null hypothesis is what would be expected under random conditions. The opposite of that would be that we believe that something has happened and these conditions are not random anymore. And so we want to test to see if this is something that's happening by chance or if it's something that we think has taken that randomness out. So let's go back to our test that we started with about the student test scores. Let's say you have the results from this test, okay, and the scores are given to you on a T-score system, and remember this is similar to a Z-score, except it doesn't have negative numbers. the national mean on a t-score is always 50, and the standard deviation is 10. Okay, so it's okay if you don't remember this. I think it was back in Module 3, and those modules are open. It's real easy to convert z-scores to t-scores and vice versa. Let's say at your school you had 900 students, and their mean was 51.1, and a standard deviation of 10. Further, your statistics class that you have disaggregated out had 25 students in it, and they had a mean of 54.2. Did the students at your school score higher than the average student testing? And our second question is, did the students score higher, did the statistics students score higher than other students in the school? Okay, so those are the two things that we want to look at. So two separate tests. Did our students overall score higher than the national test, national average? And did our statistics students score higher than other students? So at first we look at this and say, well, the answer is yes to both of those. But we want to see if this was by chance or if these are statistically significant, going back to that term. Okay, so what do we mean? So let's talk about what we know. Our givens are that our population mean was 50 and our standard deviation was 10. Okay, at your school, so we're taking our sample of our students at our school, our sample mean was 51.1 and our standard deviation was 10, and we had an N of 900. We had 900 students testing. We're considering our school as a sample of the whole population, and our standard deviation is the same. So we'll use the standard error of the mean that we did in our last module, because we're going to work with z-scores again, and we need to know the standard error of the mean. And I'll show you those formulas again. So we want to start off by looking at our standard error. So here's our formula. Standard error equals the standard deviation divided by the square root of n. So our standard deviation was 10, and our n was 900. So that equals 10 over 30, or 0.33. So our standard error is 0.33. Now, we need to find that in our population. Okay, and so that's what we've done. I mean, not our population, our sample. Our students are our sample, so we need to find that within our sample. And so, now that we've found that, let's look at the z-score formula. We're going to change this slightly, and what you're going to see is this is actually what we call a z-test. In order to use it as a z-test, our z-score formula, instead of x minus x bar over standard error, becomes x bar minus mu over the standard error, where x bar is our sample mean and mu is our population mean. So we have 51.1, that's what our 900 students scored, and we subtract our population mean from that, and we divide that by the standard error of 0.33, and we come out with a z-score of 3.33. Okay, so this shows that our sample mean is 3.33 standard deviations above the population mean. Okay, so we discussed the normal curve, and we started looking at those standard deviations so that we saw that one standard deviation is about 34%, and so forth. That's all coming into play here. Okay, and so when we have a z-score of 3.33, that means we're up really, really high on the curve. So just for your review, let's look at the normal curve again and explore where 3.33 lies. And we'll also look at the appendix that you received a few modules back that talk about the normal curve and get the percentage that corresponds to a score of plus 3.33. So if we look at this curve, we see here our normal curve, and this says plus 1 standard deviation. Really, technically, since we're looking at standard error here and using standard error, it should say +1 standard error deviation, but that's fine. The main thing is you understand what we're saying. So once we have converted this z-score, we can put it on here, and the national mean would be at 50, and our population mean would be at 51.1, and 51.1 would be here. And we know it's here because we're 3.3 standard deviations away from our national mean. So we could add these percentages together and say that on average our students scored higher than all these other students. But let's look at something here. So if we look at 3.3 on our standard deviation chart, we come down here and we see 3.33, and we come over and it's 0.4996. If we subtract this from 0.500, because that's in the top of the curve, we get 0.006 chance. And what we're saying now is there is a 0.006 chance this was not a random event. 0.006 is less than 0.005. And we're going to see that 0.005 is going to become one of the main establishment points for testing whether something is significant or not. Symbolically, we would say P is less than 0.005. Because this probability is so small, we would say this is not random. In other words, we would accept the fact that on average, our students scored significantly higher than all the other students in the country on this test, based upon their score of 51.1 being the mean and the national mean being 50. And we were able to do this by looking at these z-scores where we found the standard error of our sample, and then we subtracted our score, our mean, sample mean, from the national mean and divided by that standard error and got our z-score. So what that's showing us is that our students scored significantly higher than the national students. So that was one question. So the next question then, so did the students at your school score higher than the national average student test? The answer is yes. Okay. Now we would write that differently and we'll figure that out later, but the simple answer is yes. The next question then said we had 25 students in a statistics class that had a mean of 54.2. Did the statistics students score higher than the other students within our school? So we would do the same thing here. Okay? But our population has now changed. Instead of the national population, we're simply looking at the school population. And our sample has changed. Instead of our sample being the school, now our sample is the 25 students in our statistics class. So our standard deviation was still 10, but our n has changed. So our standard error becomes 10 over the square root of 25, or 10 over 5, or 2. So our standard error is now 2. And as a result, before it was 0.33. As a result now, when we take our sample mean and subtract our population mean and divide by our standard error, our sample mean is 54.2, our statistics student. Our population mean is 51.1. That's the students in our population, and we've redefined our population as the 900 students in the high school. Okay, and we divide those by our standard error, and our z-test score comes out to 1.55. Earlier it was 0.3 or 3.33. Now it's 1.55. So let's put that up on our chart, and we see that earlier when we were over here, now we've moved to the left. We see that 1.55, if we go to our z-score chart, we see 1.5. If we scoot over to 0.55, we get 0.4394. So 1.55 is equal to 0.4394. If we subtract that from 5,000, 0.500, we get 0.0606 chance this was not random. So now it becomes interesting because this is more than our previously established 0.0005. Symbolically, we would say P is greater than 0.0005. And because our probability, P is probability, our probability here is too large. So the 0.0606 chance that this was not random means that there is a 6% chance this was not random. Because we had established earlier the 0.0005 level, and that's what we were looking at, we're saying that we want to make sure that it's a 5% chance or less that it's random. And because this is greater than, we can look at it and say the statistics students are performing better, but statistically significant at a 0.5% level, we cannot say that. So therefore, because this probability is too large, 6% is greater than 5, we would say this was a random event that the statistics students scored higher than the other students in the high school. So it's an interesting thing to look at this when we're looking at these two examples, because the school as a whole was only 1.1% higher than the national average, and we said that was statistically significant. But when we're looking at our sample within our schools, we see that it's the difference of 51 and 54, but yet we're saying that's not significant. Okay, so this is going to bring up some important concepts here. Again, the statistical significance. The reason we use this is we're saying that under random conditions, the phenomena we're examining would not have occurred. In other words, our null hypothesis is what we would be expected under random conditions. So in that previous example, our null hypothesis would have been there is no difference between the scores on the national test of students in the statistics class and all students at Central High School. And we showed that even though it was close, we could not reject that. We said there was no difference. Okay, so that's basically what we're saying. So I was saying that we're talking about 5%. So this comes into what we call significance of probability, or significance probabilities. Statisticians usually use 0.05 or 5% and 0.01 or 1% probabilities to measure significance. Whichever level we choose, we're saying there is a blank % chance of the difference occurring at random. So 5% chance or 1% chance, or even a 0.1% chance, meaning we're saying this would only occur at random 1 out of 1,000 times. Okay. In practice, these levels of hypothesis testing must be decided before the test occurs. So we must decide if we're going to use a 5% rule, a 1% rule, a 0.1% rule, or even a 10% rule. Now, if we had used a 10% rule instead of 0.05 or 0.01, if we had said this should actually say 0.01 for a 0.1% chance. But if we had said a 0.1 or 10%, then we would have rejected that null hypothesis and said there is a difference between statistics students and all students together because the 10% rule, the 6% was smaller, and so we would have rejected our null hypothesis. So then these decisions are made before the test. If we set the school level at 0.01 level instead of 0.05, we would have said there was no difference between our students and all students in the country. If we had set the in-school level at 0.1, 10%, instead of 0.05, we would have said there was a significant difference between the statistics students and all students in the school. So why not then, after we run the test, just change what our significance level is? This is actually considered poor statistics, okay? And what happens when we start setting this, and this is going to quickly get into stuff beyond the scope of our course, but we actually run into possible types of errors when we set them either too high or too low, okay? But in general, just know that typically we start out with the preset statistical level in mind, and we might make some statement that while it appears students are scoring better in the statistics class, there is no difference at the 0.05 level. Okay? So, tests for hypothesis significance. You actually just went through and learned your first test, and this we call the z-test of significance, where we looked at our z-score and we subtracted our sample mean from the population mean and divided by the standard error, and we're able to compare z-scores to our population mean, however we defined our populations. So we looked at our sample means and we looked at our population means, and we were able to see if there was a difference and how much that difference was, and whether or not it was significant at the 5% or 1% level. And so you actually have learned how to conduct your first test of significance in statistics, and that's your z-test. Okay. So while you did that, in actuality, we have what are called one-tailed and two-tailed tests. An example of this would be the question we asked if the difference was higher than the national mean. Okay. When we specify that the difference is higher, then we're looking to see if our students scored higher on the curve. It would be to the right, far enough to be significant. Okay. By asking about the higher piece, we're looking at the upper tail of the curve, and so we would want to conduct a one-tailed test. And there's going to be a difference in how we interpret our findings depending on whether it's a two-tailed or a one-tailed. This changes the chances of rejection of the null hypothesis because it changes our z-scores. We could have asked if there were any significant differences at all, meaning higher than the national mean or lower than the national mean. And in order to understand this, let's look at this test here. So in that one-tailed test, the area of rejection is the 5% or 0.05. This is beyond a z-test value of 1.645. So if we had done the z-test in that one-tailed test, and if we had gotten a z-test score of 1.645 or higher, this would have been within that 5% beyond the curve. This is the one-tailed test on the left. And we would have rejected our null hypothesis. Okay. If we had said the students scored significantly different and didn't indicate whether it was higher or lower, then we would have been going for a two-tailed test. And you see that what happens in a two-tailed test is we take that 5%, but we divide it by each end of the curve. And so now our z-score for significance changes to 1.96 on each end. Okay? These z-scores are called critical values. And we're going to use that term quite a bit in the second half of the semester as we start looking at critical values for different types of tests. So the z-test critical values are right here. Okay, the 5% one-tailed z-test critical value is 1.645. The 5% z-test critical value for a two-tailed test is 1.96 and negative 1.96. And generally this is expressed as the absolute value of z, so that you don't have to worry about the plus or minus 1.96. So with that said then, why not, let's go back to our question we asked earlier, why not just push our test out to say 10%, and so that we could say this is significant within 10%. So the last thing we're going to look at are errors, and there are two errors in dealing with statistics, a type 1 error and a type 2 error. Okay? Because we still have the possibility of wrong conclusions, even at the 5% range, we have the possibilities. We have to discuss errors again. Remember, there's a 5% chance that we could be wrong if we set our level at 0.05. Okay? And so we're saying that we're going to accept that 5% chance that we're wrong, and we're going to reject our null hypothesis, and we're going to accept our alternative hypothesis that this is not random, whatever it is that we're studying, and that whatever the treatment was, maybe it's a new math program, actually made a difference. Okay? And so when we do that, there are two types of errors. So the type 1 error is when we reject the null hypothesis, and it should not have been rejected. In other words, we accepted our hypothesis as being true. We set the predetermined significant level before we do the analysis. We said that earlier, and we're going to stress it again here. This is indicated, I don't know what how dented got in. This is indicated by the Greek letter alpha, which looks kind of like a fancy A. So we would say that our alpha is at 0.05. This means that we have a 5% chance of creating a type 1 error. If our alpha were at 0.01, then we agree to have a 1% chance of creating the type 1 error. And again, what the type 1 error means is that we rejected our null hypothesis when we should have accepted it, and there was no significant difference, even though we think we found one. So what we see then is the larger the alpha, the greater risk of the type 1 error. So statisticians generally keep the alpha low to 0.05, 0.01, or 0.001. So in that example where we looked at the 25 statistics students, if we had set our alpha at 0.1, the 10%, then we would have rejected our null hypothesis. But we also have a 10% chance of that not being the case, and there actually being no difference in our statistics students. Even though they scored higher, there's no statistical significance in their higher scores to show that they scored significantly higher. So why not just keep the smallest number then? You know, if we want to prevent ourselves from committing these errors, why not just go to the smallest number, and let's say we're going to do the 0.001, so that we are saying there's only a 1 in 1,000 chance that this was random. Well, at that side, we're in danger of committing a type 2 error. Okay, a type 2 error occurs when we have a false null hypothesis and it is not rejected. In other words, we say there was a random chance of something happening, and it was not random at all. It was actually significant. Okay. Type 2 errors are controlled by beta, the Greek letter beta, and actually type 2 errors are a little bit beyond the scope of this course, but I did want to introduce them to you. And if you fall in love with statistics and take another statistics class, you will come in contact with beta and how to control for beta. But let's look at the consequences of these decisions. Okay, so for example, let's say you're a principal and you want to know if there's this new math program that somebody found at a summer conference will make a difference in math scores. Okay, they come in, it's all great, you want to see. You have data of your student math scores for the past 5 years, and your data show that you have had a mean score of 80 on your state assessment. Let's call it the state test. Okay, So you want to see if there is a difference. So you're going to conduct a pilot study or an experiment with the new program, and you randomly select 152 students to participate in the math program. Let's say you have a large district, and so you've selected 5 classrooms around the district, and that's how we got to 152 students. Okay. So your hypothesis then, denoted down there at the bottom as H sub 1, that's our alternative hypothesis, is the students in the new math program will score higher on the summative assessment for math as measured by the state test than students not in the new math program. And we simply write that as H1, our population mu, our population mean is greater than 80. Our null hypothesis, because we're going to say the opposite, that's actually what we're going to test, is that our population mean equals 80. Okay? So if the program shows significant results, then we will purchase the program at $4.95 a student, and depending on the number of students, per student per year, this could cost the district, let's say we have enough students that it's going to cost the district $15,000 a year. And so you're the principal, and you're going to set this experiment up to see if it actually works. And you could do this, okay? So what if we set our alpha at 0.05, and there was actually a chance we hit the 5% that were random in our selection of participants? In other words, we set our alpha at 0.05, a decent alpha, kind of on the high end of statistics, as we said earlier, but it's decent. What we're saying is we're willing to accept the 5% chance that what we saw was not random, and actually the participants we drew were in that 5% chance. Okay, and we showed that there was some statistical significance when in reality this was that 5% chance. And we reject our null hypothesis, we purchase the program, and we start paying $15,000 a year for this program, when in reality there's no significant difference. Okay? That actually what happened is our alpha at 0.05 was set too high. If we had set it at 0.01, we would have caught this. Okay? We have committed a type 1 error here. In other words, we rejected our null hypothesis, and the consequence of this is that the district is going to start paying $15,000 a year for a program that has no significant impact. Okay, that's a type 1 error. And we could have prevented this from setting our alpha lower to 0.01. The type 2 error would be if we accepted the null hypothesis. Okay, because we did not see any difference in our pilot study when compared to our previous 5 years. But in reality there was a difference, and it was just simply masked by that random participants who we chose. Okay, what happened was we accepted our null hypothesis. We choose not to purchase the program because we did not see a difference, and the students are going to remain as they are. Okay, they will be no worse off than they were originally found. This is an example of a type 2 error. Okay, so depending on what it is that we're looking at, the type 1 errors can cost you some money. The type 2 errors are going to remain status quo. But status quo could be pretty bad. So anyway, these are the types of errors: rejecting or not rejecting the null hypothesis when the opposite is true. This little chart shows you a summary. If we reject if our null hypothesis is true, and instead of accepting it, we reject it, we've committed a type 1 error, which means our alpha is too high, and it may cost us some money. If our null hypothesis is false, and we reject it, then we have committed no error. If our null hypothesis is true, and we do not reject it or we accept it, then we have committed no error. Okay? If our null hypothesis is false and we accept the null hypothesis, then we have committed a type 2 error, but the bottom line of this is that things will remain as they are. Okay? So that's a bit of a summary then of what we're going to discuss in this module on hypothesis testing. So remember, we never prove anything. Okay? That is why we express our results in probabilities. Something was significant at the 0.05 level means we are saying there is a 95% chance this was not random. So we never prove anything. We might get to this was 99.9% chance it was not random. And we might even say 99.99%. But we're never going to say 100%. Okay? So let's review what our goals were. We said we were going to use the sampling distribution characteristics to test hypotheses about differences between sample and population means. That's what we did with our national test scores on the math and the statistics students. Distinguish between a null hypothesis and the alternate hypothesis or alternative hypothesis. Define the significance level of a statistical test at the 0.05 significance level or the 0.01. Distinguish between a 1 and a 2 statistical test and know when each is used. Define and contrast type 1 and type 2 statistical errors. And then finally perform the steps of a z-test of significance at a specified alpha level. So you're going to do a little bit of work with these things in mind. And if you have any questions, as always, feel free to email or call me or text me or stop by the office.